Hello, I'm Harrison Williams, and I'll be presenting a preliminary study on cellular automata simulations for microstructure estimation during wire arc additive manufacturing. First, I would like to thank Dr. Matthew Pretty and the Computational Mechanics and Materials Research Group for guidance throughout the semester. This work aims to simulate the microstructure evolution and mechanical response of metallic components with a three-dimensional multi-scale framework using the cellular automata method. At the core of every three-dimensional CA, there is an idea of a physical space separated into individual cells. Each cell has a predetermined or randomly generated discrete state. Through each iteration of the simulation, the state of the cell updates based upon the neighborhood cells. The effect the neighborhood cells has on each update is determined upon a transition rule. The variance of transition rules makes CA a very adaptable method. Many other methods are used for modeling microstructure evolution at the mesoscale level. Of the three listed below, CA is a chosen method because of the discrete nature allows for parallelization and light computation to create a multi-scale framework. Scalable CA code is of utmost importance to the coupling of CA and macroscale methods. The CA library for supercomputers and high-performance computing systems, otherwise known as CASUP, is built using modern Fortran coarrays given a parallel structure to work with MPI. Below is a preliminary simulation of the formation of cleavage fracture in polycrystalline microstructure. It can be shown in figures 3A and 3B, the grain, size, shape, and morphology, and boundary. And in figures 3C through 3F, the stages of fatigue crack during the solidification process. Thus far, a preliminary investigation of CASUP and the modeling of recrystallization in Fortran coarrays has taken place. The library was under maintenance until spring of 2020 and ran on the Intel Fortran compiler 16. Future work consists of updating the library to a current compiler version, assembling CAFE, and developing a CACPFEM multi-scale framework. CAFE is a well-established three-dimensional multi-scale framework to predict deformation and fracture using couple methods, CA and finite elements. The simulation will use 4 MPI processes and 4 Fortran coarray images. Stored in an MPI rank, a processing element contains finite elements and microstructure coarrays that transfer data between finite elements and CA. The couple methods CA and crystal plasticity finite element method forms the crux of this work. An outline of CACPFEM is shown below, as the CPFEM solver accounts for heterogeneous deformation, while CA is assigned to dynamic recrystallization evolution. Abacus will pass grain interior and boundary to the CA model. The CA model defines state variables as grain orientation, dislocation density, and plastic strain. The relationship between Rx and CA transition rules becomes quite apparent as DRX proceeds via nucleation of grains and growth of nuclei. Transition rules predict the locations of neighborhood cell consumption and morphology of deformed grains using grain size, shape, morphology, and phase volume fraction as parameters. Data from the microstructure evolution step is then passed through the CPFEM solver to reach the following output. In conclusion, the CA method will be used to better understand and ultimately predict local mechanical properties. Once again, I would like to thank Dr. Matthew Pretty and the CMML group for the ongoing support in this study. Any questions or comments are welcome, and I will do my best to answer them. Thank you.